All right, hi everybody. We're going to talk about periodicity today. So the question that we're going to try to answer is, what is meant by periodic trends in the periodic table? Why is the periodic table called a periodic table? Why isn't it just called the table of elements? So what does that idea of periodicity mean? So there's two things I want you to do before I really start getting into things. Number one, I want you to have your periodic table out. So have that handy so that you can be referencing it. I also want you to have your box chart handy. I have a gold version of the box chart, but some of you have like a PDF or a printed version of it. Have this out just so that you can take a look at it as we're going. All right, so what I'm going to talk about right now is a little bit of review from the electron orbitals notes that we already took. But now we're going to see if we can figure out electron orbitals without having to use the box chart. So what I want you to see is as you're looking at your periodic table, and you could totally just write this on your periodic table. We really encourage you to take notes on your periodic table so you have a little bit of a cheat sheet during the test. So instead of having to look everything up on your box chart, which you could if you wanted, I want you to notice that the numbers 1, 2, 3, 4, 5, 6, 7 that are going along the left side, those are the principal energy levels. So when I see a 1, I know that right next to it, it's the principal energy level is going to be 1, 2, 3, 4, 5, 6. Okay, that seems kind of obvious. It gets a little bit more complicated than this. All right, so then the different colors represent the different energy sublevels, S, P, D, and F. Be careful because notice that the S's fill first, the P's are over here, the D's are in the middle, and then the F's are all the way at the bottom. So you definitely can and should label your periodic table SPDF so that you know where they are on the periodic table. And then I'm going to add a little complicating factor. That one's fairly easy, but this is a little bit annoying. Notice that the principal energy level off to the left, so look at in the yellow column to the left where those numbers are. Notice the number 4. Pay attention to that one. Now look across into the blue D area. Notice what the number is. Unfortunately, it's not 4D, it's 3D. Joke's on you. So anyway, there are reasons for that. I'm not going to go into all the details right now, but just be aware of that it's 3D, 4D, 5D, 6D, and then 4F, 5F when we're talking about the Fs. It has to do with the way that the periodic table is actually set up with the lanthanide and actinides cut out. Okay, moving on. So let's talk Mendeleev. So you should have already watched the crash course video about Mendeleev. He's a super interesting character, and yeah, just this contribution that he made to chemistry is incredible. So Mendeleev created the periodic table, as you know, based on placing elements with similar properties in a group. And the thing that was really amazing is that he was able to take his periodic table and predict the properties of elements that had not even been discovered yet. So here's an example, and my picture is a little bit in the way, but here's an example for germanium. We now call it germanium. I'm trying to scoot my picture out of the way there. There we go. So he predicted that it would have a density of 5.5. Its density is 5.47. I believe that's grams per centimeters cubed. It should have units on it. Melting point, he thought the melting point was going to be very high. Formula when it's combined with oxygen, and formula when it's combined with chlorine. And he was spot on with those. So that's part of the genius of this periodic table. And oh my gosh, talk about genius figuring this stuff out. All right, so these are some of the periodic trends that we see in the periodic table. So periodicity, going to move me again. Periodicity is the study of patterns in the properties of the elements. And we're going to talk about some of them, not all of them, but we're going to talk about some of the periodic trends. And these are things that Mendeleev figured out. So what are these patterns? The patterns are, for the most part, based on the elements' electron configurations. So that's why we study the electron configurations first. The number of energy levels occupied and the number of valence electrons is what determines most of them. So the first one we're going to talk about, and you should write this down. Atomic radius is defined as half the distance between the nuclei of 2 atoms of an element. What? Okay, 2 atoms, half the distance between their 2 nuclei. So here's 2 atoms, here's the nuclei. The full distance would be like a diameter, half the distance is a radius. So that's the definition, is an atomic radius. Okay, so notice, I'm going to get me out of the way again. Notice what happens to the radii as you go down and as you go across. Down is kind of obvious. So as you go from the top to the bottom, the atoms are getting bigger and bigger and bigger. The radii are getting bigger, and that seems sensible. The part that can be very puzzling is the fact that as you go across the periodic table, they actually get smaller. So what could possibly be accounting for them getting smaller? As you move across the periodic table, we are gaining protons and electrons. Why would the atom diameter, why would the radius be getting smaller? Well, there's a few reasons. So as you go top to bottom, the electrons are added to increasing principal energy levels. So these energy levels are farther away from the nucleus and give it a larger radius. Makes sense. As you're moving from left to right, am I going left to right? Yep, this is my left, this is my right. As you're going left to right, electrons are added to the same principal energy level. So they're not being added out here and then out here and out here. They're being added in the same area. Okay, that's important. More protons are being added to the nucleus on the inside, and protons are attracted to electrons. The electrons aren't being added out here. They're being added as you go across. They're being added in the same place, and now the nucleus is getting stronger and stronger. The pull of the nucleus is getting stronger and stronger. So that pulls those electrons that are all in that one shell, that pulls them closer and closer together until there's no more space. That radius now has gotten so compact, that atom is so tiny, there's no more room for another for another electron. So then I'm going to go back a page. So then I'm trying to go back a page. If you look at this diagram, look at, say, neon all the way. It's like a teeny tiny little dot. Those electrons are just packed into this tiny little, there's no more space for another electron. So the next element is a crossover on sodium. Notice that sodium is way bigger. That's because we couldn't add an electron here. So now the next electron had to be added in a next shell outside. And so it gets bigger. After you get to the noble gases, that's the smallest it can be in that row. And then when you get to the next one, it gets a little bit bigger. All right, so make sure you feel confident on that. So electrons are added to the same principal energy level as you're going across. More protons get added to the nucleus, and that makes the nuclear charge stronger, which pulls the energy level pulls the energy levels in closer, pulls the electrons in closer. I don't know why it says energy levels. Okay, the next periodic trend that we're going to talk about is ionization energy. Ionization energy, and this is one you're not going to know the definition of unless you write it down. The energy change that accompanies the removal of an electron from an atom. I don't like the name ionization energy because it doesn't feel very intuitive to most people. An ion is an atom that has gained or lost electrons. So what we're talking about is specifically losing an electron. And I want you to predict this for a second. If I go up to a sodium, look at where sodium is. Sodium has one electron in an s orbital. If I go up to sodium and I try to pluck an electron off of it, is that going to be easy or hard? In comparison to if I go to the element just before it, neon, which is a noble gas, it's a tiny, tiny, really compact atom, and I try to pluck one of its electrons that are super close to the nucleus, which one's going to take more energy to pluck that first electron off? Well, okay, so you can guess that it's going to be easier to pluck an electron off of sodium than it is to pluck it off of neon. So as you're going top to bottom, the ionization energy decreases. What that means is so if we go all the way to the top, hydrogen has one proton and one electron traveling all around it. It's fairly close to that proton, and so it's experiencing the draw of that proton, and it's difficult to pluck that one electron away because that proton is really holding it tight. But by the time you go all the way down that column and get to francium, francium's outermost electrons, if this is the nucleus and the protons are here, trying to get my hand in there. Francium's electrons, the valence electrons, are way far away. And so the protons don't have much of a pull on them. The gravity sort of doesn't pull very hard. And so we're able to pluck those electrons away without too much resistance. They are so far away from the pull of the protons in the nucleus that they're easy to pull off. So the ionization energy is very low at francium and very high at helium. It would be at helium also, but even higher, but at hydrogen. All right, so that's top to bottom. So it's the lowest down here, and it gets harder and harder to pull the electrons as you get smaller and smaller atoms. Now, left to right, the ionization energy increases. So as we're going this direction, it gets harder and harder to pull the electrons off. That's because the atomic radius is getting smaller, and it'll explain on the next slide. So I forgot it explains it. Okay, so as we go top to bottom, we have something that's called the shielding effect. So this is where we're comparing hydrogen and francium. So the shielding effect says electrons that are farther away from the, gosh, I'm trying to get my hands in the image here. Electrons that are farther away from the nucleus have less attraction. They are shielded from the nucleus by other electrons that are in the way. So those far away electrons, super easy to pick off. Francium has a bajillion electrons that are super far away. They don't take much energy to pluck them off. All right, less attraction means easier to remove and therefore lower energy. However, as we're moving from left to right, atoms to the left have low energy due to a larger atomic radius. So remember, sodium had a pretty big atomic radius. It has that one electron that's floating around in an S shell because it couldn't fit into the neon tiny, tiny little atom. So it's way out there, and so it's easy to pluck that sodium one electron off. However, as you start moving across, remember that the atomic radius starts getting smaller and smaller because we're adding a proton each time. We're adding an electron and a proton. With each move over in the periodic table, we're adding a proton and an electron with each new element. And so that means that you are making the nucleus stronger and stronger and stronger. And so it's pulling those electrons in closer and closer and closer. And then it gets harder and harder to pull those electrons off. So imagine like a stronger and stronger and stronger magnet. I know this is an analogy. It is not really what's happening, but imagine the nucleus is a bunch of magnets, and the more magnets you add to the nucleus, the stronger the pull is as you're going across. So everything is getting pulled in tighter and tighter. All right. This is a video that I'm going to have you watch later. I'm not going to watch it right now. It is a really fun video, but I don't want to take the time to do that right now. So super cool about periodicity and the alkali metals. This is a chart of ionization energies, and it shows super interesting periodic trends. So if you notice, start on the far left, and we've got hydrogen first, and we're going across the periodic table. So hydrogen, and then let's see if I can hold this up. Hydrogen is here. Trying to do this right. Hydrogen is here. Helium is over here. So now look at that on the chart. Do you see where hydrogen is on the far left? And then helium shoots up. Helium is a noble gas. Hydrogen is fairly hard to pull its electron off of. It's fairly hard. But the helium, it's even harder to pull it off because that's a noble gas. It's really tight. Those electrons are super close to those two protons. So its ionization energy is super, super high. But when you go to the next element, which after helium, the next element is lithium. Lithium has 2 electrons in the first shell and just 1 floating around in the outermost shell. It's a longish ways from the nucleus. And so it's really, really easy to pick off. So we say that its ionization energy is super low. We could pluck the lithium electron off very, very easily. That actually has to do with lithium batteries as well. Okay, and then as you move across the periodic table, it's not a perfect line, and there are some reasons for that. There are some advantages to having a half full shell or a full shell. Don't worry about it. The general trend is that it starts getting harder and harder and harder and harder to pluck it off until you get to the noble gas. Look at neon on your chart. Look at neon on the line chart. Do you see that it's really high, the line graph? You see that it's got a fairly high one. And then when you go beyond neon to sodium, suddenly it's really easy to pluck it off again. And as you move toward getting closer and closer to the next noble gas, it gets harder and harder, and then it's easier. All right, you're getting the idea. Now here is a fascinating little problem. Successive ionization energies. What if you don't want to just pluck off one electron? What if you want to pluck off the second or the third or the fourth or the fifth? Well, there's different ionizations for each electron that you pluck off. So let's look at sodium. Let's just take a look at this diagram right here. As you're reading across the top, it says element, and then it says I1, I2, I3. I1 is the first ionization energy, I2 is the second ionization energy, I3 is the third. So we're saying if you plucked off one electron, if you then went to pluck off the second electron, if you then tried to remove the third electron, how much energy does it take to remove those? So what I want you to notice is that for sodium, the very first element that's mentioned, it is a fairly low ionization energy. So it's 496. The units are kilojoules per mole, which right now you probably don't know what kilojoules are, and you probably don't know what moles are, but whatever. It's just an energy amount. Good enough. 496 energies. Okay, but then after it's got 11 electrons. When you pluck off the first electron, it now has 10 electrons. 10 electrons is what neon has. I hope you're looking at your periodic table at the same time that I'm talking about this. Neon is a noble gas. So now this sodium has an extra proton and the same number of electrons as neon. That means it's ultra stable. And so if you want to pluck away the second electron so that it would only have 9 electrons left, you're going to have to use a buttload of energy. Look at how much the energy increases, how much more energy you need to use to pull off that next electron. Excuse me. So for sodium, plucking off the first electron only required 496 kilojoules per mole. To get the second electron, which actually was in a noble gas for conformation, it takes 4,560 kilojoules per mole. All right, let's move on to magnesium. So magnesium is next to sodium. I'm hoping you can kind of even predict what's going to happen here. So for magnesium, for us to pluck off magnesium, it's fairly far away from the nucleus. It's not anywhere close to a noble gas configuration. So we can pluck off that first electron fairly low energy. It's not too much. The next electron, we're having a stronger pull of the nucleus because we still have all of the protons. So magnesium normally has 12 protons. If we pluck off the first electron, we still have 12 protons, but now we've got 11 electrons. So that nucleus is pretty strong. If we go to pull off the third electron, try to pull off the third electron, it now will have the same number of electrons as neon does. It's now got a noble gas configuration in terms of its electrons, and it has 12 protons instead of neon's 10 protons. So the nucleus is stronger, and it's got completed orbitals, and so it's got the noble gas configuration. So notice what happens on the ionization energy number 3. The number suddenly skyrockets. The amount of energy it takes to pluck off the third electron from magnesium is enormous. So now I want you to take time, maybe even pause this video and look at aluminum. Where does aluminum become super, super hard? It's in blue. Why did it become so hard to pluck off the fourth electron? Look at your periodic table and see if you can make sense of that. You will absolutely have to figure these kinds of tables out on your test for this unit. All right, multiple ionization energies. There is an ionization energy for each electron of an atom. This is what I've already said. For example, each carbon has 6 ionization energies, 1 for each of the carbon electrons. Ionization energy always increases for each electron removed, and that's because the protons are staying, there's the same number of protons. So if I have 6 electrons for carbon and I have 6 protons, if I take away an electron, I still have 6 protons. So the protons are stronger than the electrons right now. So more protons than electrons as they are removed. So that means a stronger pull by the nucleus. The largest increase in ionization energy, the time that it becomes super hard to pluck off that next electron, occurs after an atom reaches a full energy level. In other words, it becomes like a noble gas. For example, take a look at barium. So barium is right here. It's kind of like the magnesium one that I just gave as an example. So barium has 2 electrons in its outermost S shell. So it says barium's largest jump in ionization energy values will be between its second, so you pluck off those first 2 and it's easy, but that third one, so between its second and third ionization energies, the jump is enormous. This is due to the fact that once it loses its second electron, It's now just like xenon, a full and stable level, and, which is a noble gas, and it doesn't want to lose a third electron. Ladies and gentlemen, that is the end of our notes. I hope it wasn't too torturous for you. Have a good night.